Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. The last lecture what we have seen is mapping between two different frames where both translated and you can say oriented. In the sense the mapping between you can say two frame we have seen in different way. So what we have actually seen that we would be continuing, but what exactly here we are continuing is basically one additional aspect called transformation matrix. We will bring it. Why this transformation matrix and why it is called homogeneous and how this can be used as an operator further. This is what we are going to see in this particular lecture. So if that is the case, we will actually recall where we stopped. So we have actually seen that there is a position vector of q with respect to b is given if the positional information of b with respect to a and the orientational information of b with respect to a is given, we can find this position vector, right. So this is what we have seen in the previous lecture. So now we imagine there are actually several bodies associated like this. So for example, this is a body 0, 1, 2, 3 like that keep going. So here actually like shown it is something like in series, but imagine this transformation to this transformation, can I actually get information? Yes, I can do. Similarly, can I get this? So if I actually keep getting, so what you can see, this is the relation I will get. For example, now I want to find the C. So what I have to do, so position vector of q with respect to C, I have to write position vector of B with respect to A, then plus position vector of you can say you can write position vector of C with respect to A, this is the position vector. Then you can write, first you have to rotate about you call C with respect to B, then you can actually make another rotation. So what that rotation, so you can actually rotate about B with respect to A, then that would be giving position vector of q with respect to C is known, we can actually write as A. Okay. So this way you can write. So now if you write this equation, it is actually you can see complex, right. So there is one addition, so there is another addition, but it is having a multiplication. Even here you can see this is initially multiplied and it is actually added. So like that there are several you can say constraints will come if you keep increasing the number of bodies. Instead of that, can I actually make a single entity, or in the sense, so I have one body, another body, like that I am actually using as a briefcase. In the sense, inside the briefcase I would be having information about orientation and the position, but one briefcase would be simple box. So another briefcase is equal dimension, I keep it. In the sense, you can see I can actually make a stack and I can operate easily, right. So now in order to do this, what first of all you have to see, you can see here that operation is actually heterogeneous. So what kind of operation? One is addition, the other one is multiplication. So now you have to actually make a homogeneous operation. So for what we are actually trying to do, we are going to do a simple multiplication. So that is what we are trying to do. In that sense, we will come back here. So we are bringing a transformation matrix. So what that would be equivalent to an operator, it would be equivalent to a rotation matrix, but not straightforward. But what that maps one frame to another frame in a matrix form, which will give a simple aid of compact equation. That is what I said, it is something like a briefcase. So as well being a conceptually clear. So inside the briefcase you can see that there would be a positional information and orientational information. So if that is the case, I will take a very simple example, which is probably a crude example. So you can see inside the college or inside the class, so you can obviously you can find two different class of students. Okay. In fact, there are three, but I will say that majority will have, so girls and boys, right. So what if I call that group as a general as a student, you can see they are homogeneous. But if I see inside class with the gender wise, so girls and boys are actually heterogeneous. The similar way, So the matrix, you can say rotational matrix and the positional information, I take it as a girl and boy, but instead of that I am calling as a transformation matrix as a single entity, as a student. If I do, I will get what? So I can actually like pass easily one information to another information. For example, I am actually like calling probably one another institute, I am saying that this information you should pass to students, okay. But they can actually like see that the student, whether this information should pass to girl or boy, that actually like separate. But you can see like the student, if I say the student, the information should pass to student, it is actually like homogeneous, in the sense one institute to another institute or one class to another class, it is actually like student to student information, I do not bother, right. So the mode of information pass probably a simple circular or simple, you can say email or anything I can do, but inside, so the classes would be having girls and boys, right. So which is heterogeneous. So now that is the same way we are trying to do, although your transformation is consist of one, you can say positional information which is in the, you can say vector form, and the orientation information in the matrix form, but we are combining, okay. So for that what one can do, so that is why I have written the dimension also in the previous slide. So this is actually like 3 cross 1 and this is also 3 cross 1 and this is 3 cross 3 and this is 3 cross 1. I cannot actually like do it because this is actually like something like I cannot stick with the same dimension. So then what I can do, so I can increase the dimension instead of this. So if I actually like write this is 4 cross 1, where this I keep it as actually like a dash, okay. So I keep it as a dash. So in the sense PQ A dash, here something I am writing, in the sense one additional dimension is coming, okay. So then what I can see, I can bring it as one additional dimension which bring it 4 cross 1. So then this is also supposed to be 4 cross 1 later on, okay. So then this supposed to be retained as, you can say what, so 3 cross 3, then this cannot be multiplied, then it should be, so 3 cross 4. So then how I can do it? It is actually like very complex, right. So instead of that, can I actually like make it a single matrix which is transformation matrix of B with respect to A. So this would be multiplied with the outside information which is the position vector of Q with respect to B. So I can do it, right. So now this dimension should be not 3 cross 3, it should be one dimensional extra, which is supposed to be 4 cross 1, then this would be 4 cross 4 and this would be 4 cross 1, okay. So this is what we are actually like interested. So if I do this, what I can actually like, what I supposed to do it. So this is what I am actually like trying to write. So now the straightforward, this equation is not consistent, right, because in the previous lecture I said this is 3 cross 1, this is 3 cross 1 and this is 3 cross 3 and this is 3 cross 1. This cannot be consistently say this is not unit wise good. So then this is not possible. Then what we can do, so that is what we are trying to do. So we are trying to bring a 4 cross 4 matrix, and in order to make this 4 cross 4, so the position vector also would be increased by one dimension, okay. So that is what we are actually trying to show. So the representation of n component position vector would be increased n plus 1 component vector. So this is what we are calling homogeneous coordinate representation. So what that, so instead of calling girls and boys, we are calling students, the same way we are bringing it. So in the sense one simple difficulty will come that we will see. So now the transformation matrix I am writing into 4 you can say sub components. One is our rotational information, another one is positional information. In addition to that, there are 2 things are coming, right. Strictly speaking, this is eta transpose. So eta transpose is actually like written as in this way, it is a perspective vector, okay. Sigma is actually like scaling factor. So why the scaling is important? For example, if you write your position vector B with respect to A, so I can write x, y, z, okay, I am writing as a sigma. So the sigma is a scaling. So the scaling will give one additional benefit to us. What benefit would be given to us is you can actually like use any kind of unit as long these 3 are actually like same entity. So your x position, y position and z position all represented in a same unit, then the scaling can be used. Now for example, I am using the position vector of B with respect to A in millimeters, okay, but position vector of Q with respect to B in inches, but I want the information of position vector of Q with respect to A in meters. I can do it here. I can use the you can say corresponding scaling factor sigma, and here corresponding scaling factor sigma, then it would be done, right. So, that is the advantage of using this scaling factor. Okay. This perspective vector, when it would be used? So, this perspective vector would be used if we are not using orthogonal projection or orthogonal view. In the sense, for example, you are keeping a camera. So, you are keeping a camera and this camera is giving a proper perpendicular view of yours, you do not need to worry, but this camera is actually like inclined. So, it is actually like giving your view in a, you can say, perspection way. So, then this perspective vector would be used. Mainly if you look at it, some of the, you can say, computer algorithm people would be very much you can say encourage this, or you can say appreciate this, because they use this perspective vector everywhere when they do, you can say, graphics and all. So, that is what the whole idea here also. So, we will be having a perspective vector, okay. So, then you have actually like scaling factor, then your position vector and your rotational or rotation matrix, okay. So, this is what you are actually like bringing as a transformation matrix. This transformation matrix can be you can say divide into two parts. So, or decompose into two parts. What part you can see? First you rotate and then translate, okay. Since we are talking about A frame is actually like fixed, so you have to pre-multiply, but the same way you cannot do the other way around. First translate and rotate cannot be done, you know, like matrix, right. So, the matrix multiplication is not, you can say, commutative, right, in the sense. So, these two are not equal, and as per the transformation matrix, first rotate and then translate. So, in the sense you have two coordinate frames, okay. So, first you have to actually like rotate this parallel to this, then you translate, that is the meaning of this, okay. So, now you can see like pure rotation is first, then translation. So, I hope you are clear what exactly the matrix decomposition, not this, okay. So, now we will actually like come back how this can be used as the transformation operators. So, there are actually like several options. So, I have taken one simple idea to understand. You can see this is one body and this is another body and this is the third body. As I already said, can I write the transformation matrix as a box and I can pass the information? Yes, I can do. So, in the sense what you would be knowing? So, you would be knowing the transformation matrix of B with respect to A, you know the transformation matrix of C with respect to B, okay. So, even if I know the transformation matrix of you can say C with respect to A, so what I can do? I can actually like simply I commute, in the sense I just multiply. So, this will be actually like obtainable, right. So, this is what we actually like call the transformation. Now, for example, this position vector of Q with respect to C is known and the information of these two transformation matrix is known. What I can do? I can get this very straightforward. The position vector of Q with respect to A can be written as the transformation matrix of C with respect to A multiply with the position vector of Q with respect to C. But this is actually like can be written as this form, right. So, if I write this, so what you know the transformation matrix general, okay, it would be a rotational matrix and position vector, and conventionally we assume that there is no perspective, in the sense the perspective vector would be we consider as actually like 0, in the sense it is always orthogonal view, and we always assume that the it is for, you can say, lecture, we always assume that everything is in a single unit, in the sense the scaling factor is 1, okay. So, this is what I want to say. So, this is actually 3 cross 3 and this is 3 cross 1 and this 1 cross 1 and this entire thing 1 cross 3. So, if I use that, so what I will get? The rotational information compound rotation can be written in this form and this can be expanded in this form. Once we know these two can be written the you can say transformation matrix of C with respect to A in this way, and this is what the final matrix. You can see like now it is easy, right. So once you know this box and this box, you just post multiply and you get it. Okay. So now this is what the final matrix. You can actually get it. Now this can be used as a simple, you can say, compound transformation tool. So that is what we have used. Now the next case is, if you know the transformation matrix of A or transformation matrix of B with respect to A, can I get transformation matrix of A with respect to B? So this is nothing but this inverse, can I get? So this is what the second tool which we are going to use. Okay. So that is what we are going to use. For that, what one supposed to know, so this product would be giving identity matrix, right? So that is the algorithm, or that is the logic we are taking. So this product would be identity matrix. So if we assume that, this information is actually like unknown, in the sense the transformation matrix of A with respect to B is unknown, but transformation matrix of B with respect to A can be written this way. Okay. And this is a big 0, which is 1 cross 3, and this is 1, and transformation matrix of A with respect to B, in the sense transformation matrix of this inverse, would be having X as the bigger fact and Y is the another fact, and this is 0, which is 1 cross 3, and this is 1. So what I can do, I can actually like multiply these two matrix and equate to identity matrix, right? So that is what we are actually like going to do. You can see. So this is another subset of identity matrix, and this is one scalar. So and this is 0 vector. Can I actually like multiply? If I multiply, what I will get, this is the first term which is equivalent to identity matrix, and this is the second term, this is equivalent to 0 vector. So in the sense, I can actually like rewrite this. So from this, so what one can see, X can be written as, so RBA inverse into identity matrix, but identity matrix no need to inform because this is a matrix. So then what you can write, this is RBA transpose, because we know that the determinant is 1. So in that sense, X can be get like this. So similarly, Y can be obtained. So how? So you can write, so this is actually like RBA equal to minus X, then Y is actually like minus RBA whole inverse into Y, and this is equivalent to what? So I am writing Y is, so R minus transpose into BA, right? So this is the case. So now you can see like these two obtained. So now X and Y. So what one can actually see, this can be as an operator. So this is what the idea. So now you can see that we substitute that Y and X. So now it is straightforward, in the sense the transformation operator where we can use for compound or matrix inverse is actually like obtainable, right? So in the sense, what we obtain in this particular lecture, we have obtained the, you can say, transformation matrix of B with respect to A if there are frames A and B are given, right? So further in the next lecture, what we can actually like expect, how to find this rotation matrix. This is consist of compound rotation, right? In reality, what reality, in the sense, in the reality you have the one body to another body would be in space. So obviously there are 3 orientational information is known or given. How we can write this rotation matrix of B with respect to A for given, you call 3 orientational information, which is very, you can say, tricky. So there are several compound transformations are coming, in the sense it should not be called a compound transformation, although it is, but we have to call composite rotations. So there are several notations are there. We are going to use that in the next lecture. Until then, see you, bye, take care. I hope you are clear about the transformation matrix here. Thank you.